Very good morning to all the participants. I welcome you all on the fifth day of this 2-week advanced online training program on utilization of nanomaterials and instrumental technique for energy applications. Session 1 from 10:30 to 11:30 is on the topic characterization technique for oxide systems, an example with zinc oxide with the part 1 of this lecture. I'm feeling extremely privileged to welcome our technical speaker for the session, Professor Somaditya Sen, sir, Associate Professor Physics, Indian Institute of Technology, Indore, Consultant Physics Department, King Fahd University of Petroleum and Minerals, Saudi Arabia, BWC member, ABV IIIT Gwalior. He works on structure correlated properties of magnetic oxide semiconductors, co-doping in simple and complex perovskite, double perovskite oxides, and explores functionalities on the application side. Ferroelectricity is one of the most studied subjects in his group. Dr. Sen received his PhD from Indian Association for the Cultivation of Science, Jadavpur University. His doctoral thesis was on electrical and structural properties of some semiconducting alkaline earth vanadate glasses. After spending a brief period of 3 years teaching in a school in Kolkata, India, he went abroad with the thrust of better research opportunity. His passion for both teaching and research made him choose his profession in this domain of academics. He spent a brief postdoc in National Taiwan University from Jan 2003 to August 2003. During his second postdoc at University of Electrocommunications, Tokyo, Japan, he worked on synthesis and non-destructive detection, characterization of germanium nanodots. He later moved to the USA in January 2006. He worked as a postdoc fellow with Professor Nikolai Kokulin at the Electrical Engineering Department of University of Wisconsin-Milwaukee for an year on semiconductor nanomaterial synthesis and device properties. He later moved to work with Professor Prasenjit of Physics Department in the same university as a research associate and scientist. He worked on several projects related to magnetic and multiferroic materials. At this point, he got the privilege of working at different internationally famous research institutes, including Advanced Photon Source at Argonne National Laboratory, LENS at Los Alamos National Laboratory, Synchrotron Research Center of University of Wisconsin-Madison, and so on. He returned to India in January 2013 as a visiting associate professor in the Center of Surface Science and Engineering of IIT Indore. He joined IIT Indore as a permanent faculty member in October 2013 in the Department of Physics. Later, he was appointed as the Associate Dean Planning in August 2015 and then Associate Dean Planning 1 in January 2016. He also served as one of the board of governors of IIT Indore during the period January 2016 to December 2017. So we are extremely honored to have you here. Now I hand over the session to you for your technical talk.
Can you hear me?
Yes, sir.
Okay. So, thank you. This is a great privilege to participate in this program today. Thanks to Professor Ankur Jain for inviting me for this great session. It is a great effort taken by you guys, and I hope I'll be able to keep as much as possible brief but informative this session. So I will talk on oxide materials, and I'm taking a special, very important material, zinc oxide, as an example. Okay. So before I start, let me briefly introduce where I am from. I am from IIT Indore. It is a new institute. Technically, it is about 13 years old now. It is on the 13th year. It was founded in 2009 and presently it has 160 plus faculty members. Several departments are there of engineering, computer science, electrical, mechanical, civil, metallurgical engineering and material science, aeronautical and astronomical sciences and engineering. In the science and humanities, we have chemistry, mathematics, and physics. I belong to the physics department. And as you see that IIT Indore has already taken a leading role in the world universities. And it's in most, previously it used to be in 350 to 400 slot. Now it is fluctuating a little bit, but still within the 300 to 500 range. And in different subjects such as Excel, like in computer science it is. Okay. So our H index is going higher by the year. And if you consider the Department of Physics, then just give me 1 second. Yeah. Then we are actually doing quite well in IIT Indore. You can see the publications and age index of our department is the highest in amongst the other departments of IIT Indore. So you can well understand there's a research trust that we have to go through, endure during our this. This is a department, different faculty members and students are there. Okay. Now, my group is known as the SMART group. The SMART group comes from semiconduction and magnetism, advanced research and technology. What we do, we synthesize the materials using different techniques. It's just not one technique we use. So I'll come to it later on. Sol gel, hydrothermal, solid state reactions. And then what we do, we try to find out the structure using XRD and other different probes, which I'm going to discuss. So this is the initial point. 10 years back, I was only doing this part that I was not looking into the technology part. But today, because I'm working on materials like ferroelectrics and multiferroics, and also some of the photocatalytic um, uh, aspects of the same materials or photosensing, I'm looking into the device part also. Okay. Now, as you can see, this is a structure. This is a perovskite structure of one of the materials that has been synthesized in our lab. It's lanthanum ferrite doped with titanium. And you can see the different orientations of the titanium octahedra. We go to that depth where the titanium octahedra, how they tilt and how they affect the the technicality or the functionality of the material. That is our subject of research. We produce about 10 to 15 papers and average from our group. It's a very active group. It is consisting of a number of PhD students and master students and also bachelor students. And on the right side, you can see this is a ferroelectric loop. This loop is very familiar to some of you who has studied magnetism a little bit. And even if you have not studied magnetism, this type of loop is very well known in magnetism. It's a hysteresis loop. Many of you know it from class 12. But this is not a hysteresis of magnetism. This is a hysteresis of where the field is an electric field. It gives rise to polarization, and that gives rise to very exciting materials called ferroelectrics, piezoelectrics, and so on. Okay, now, as I said, the group is a very big group. Already many, 14 students have graduated as PhD scholars, 9 students as masters, and several BTech students have graduated from my lab and have secured their positions. They are pursuing their PhD at this moment at very prestigious universities like UCLA, UCSD, I forgot one name here, and IIT Illinois. This is not IIT India. This is Illinois Institute of Technology. Okay. There were women scientists working in my lab, and now presently we have 5 PhD students and 3 generally every year there are 3 master students. Lots of people come as interns. So whoever is looking for internships, just drop me an email. Okay. Okay. Now, let me start with the oxide materials. That is the bread and butter of a smart group. Now, the oxide materials that we produce range from semiconductors to ferroelectrics and magnetic materials. Okay, so it contains simple oxides like transition metal oxides like zinc oxide, titanium oxide, copper oxide, nickel oxide, iron oxide, or some rare earth oxides like lanthanum oxide. I forgot to put it here, and cerium oxide, etc. And then there are some very complex perovskite oxides, like the well-known ones are barium titanate, lead titanate, sodium bismuth titanate. These are all very strong ferroelectrics. And we try to play around with the, so in the perovskite oxide, this is the A site and this is the B site. There are two sites in the structure. I'm not going to deal with it. And we play a lot of things, try to dope the A site and B site and create new functionalities in the materials. And also we deal with manganetes and titanates. Titanates are already mentioned, and ferrites. Okay. Now, the research focus of our group is specifically on the optoelectronic part, the transport part, the dielectric, ferroelectric, and magnetic property part. And the last 4 or 5 years, we have been working very ardently on dielectric resonator antennas, which is a way to use all these oxide materials that we produce in our lab in different forms. It can be a cuboid, it can be a cylindrical form, a pellet or something like that, or a thin film, and use it to probe different frequencies, either to emit or receive different types of frequencies to propagate and to be used in telecommunication. And as all some of you may know, that all these nanoparticles of these materials are very much interactive with with proteins and other material, other biologically important materials, components like bacteria, virus, etc. So we also looking at, there's a subgroup or that is already looking into it, and we have active collaboration with 2 to 3 places, including ZnO and some of our labs in IT Indore. Now, the outline of this talk is, I'll give you a brief introduction of the oxide materials first, and then I will tell you the importance of zinc oxide in this material, why zinc oxide is so important. And then I'll go to the structure. I told you before that structure is our bread and butter. And what we do, we try to relate the structure to different functionalities. That is the prime interest of our group. Okay. So in this talk, I'll also talk about the synthesis techniques briefly. And as I said, the structure, how is it correlated to the electronic properties? And then I would say how zinc oxide can be modified by either doping or co-doping. Co-doping means multiple elements are being doped in zinc oxide to address certain issues which needs attention of all researchers at this point. Now, and then I'll briefly talk on the role of ionic size and ionic charge that is related to the previous point on the structure, strain, and the crystalline. Now, what is the importance of oxide materials? The oxide materials are actually, in nature, everything gets oxidized. Okay, so if you keep a piece of iron, it will soon rust, and rust means it has oxidized. So, but oxides, when it has formed an oxide, it is pretty stable. Okay, and that gives us the chance to work on it because of its robust properties. So most oxide materials are very structurally stable, and that's why it can give robust properties. The electronic structure of these oxides are such that it can range from a semiconducting material to a metal insulator material on one side, and also it can sometimes, if you can tune the band gap properly, then it can show metallic properties in some cases. Okay. It's rare, but it can show. Now, where is it used? It is generally as a science subject. It is used in material chemistry. As medical importance, it is used in some medicines, agriculture, energy applications, biomedical space sensors, optoelectronics, electronics, general electronics, catalysis, environmental application, and even in IT. Nowadays, they have started using different research on IT sectors also. Now, metal oxide surface is very important because the surface has a very effective interaction with any target molecule. So if you are targeting some functionality with some molecule of your choice, then the surface of a metal oxide is very much interactive. Okay. Now, the interesting part of having oxygen in the system is that it is very easy to take out an oxygen from the lattice and thereby creating oxygen related defect, or you can push in oxygen extra, creating oxygen interstitials, and whenever you do this, the lattice get disturbed, the lattice get distorted or disordered. Okay, now why is it so? Suppose there is a oxygen position and you take away the oxygen, that part is remaining vacant, and what it leaves certain amount of positive some amount of positive charge there. Okay, so that gives rise to different types of changes in the electronic configuration. Okay, so and also the empty spaces has to be filled up by some other neighboring atoms. So there is a lattice defect that happens at that point. So there's a local defect, and that gives rise to a local strain, which can get us into a different energy state created in between the band gap. So this type of defects can always give rise to newer luminescence properties. So it can also lead to band tuning to some extent, and it can also give rise to photoluminescence and other things. Here you can see that these properties that I just discussed in oxide materials can give rise to very nice functionalities, like this is current the light sensing. So light is turned on, that goes on, and then it comes down. Okay, and then we can study the physics part of it, studying the different vibrations and other things. Okay. Now, while discussing zinc oxide, I should say that zinc oxide, first thing that we need to know is zinc oxide can occur in three different stable or metastable structure forms. Okay, the most stable form is the Woodside structure, which has a space group of p63mc, and it has a. I'll show you the difference between the three structures in the next slide. And what it has plenty of defects that can happen due to either presence of oxygen or absence of oxygen, or presence of the cation zinc or absence of the cation zinc. Okay, and that gives rise to different discrete levels within the band gap, and that is a matter of interest that can give rise to different transitions of electrons from different levels, giving rise to different types of color emission. Now, in the zinc oxide, zinc is generally in the Woodside and zinc blend, it is in the tetrahedral geometry. The tetrahedral geometry has a coordination of 4, and the ionic radii of the zinc atom will be 0.74 angstrom. Whereas in the tetrahedral geometry, the oxygen is also tetrahedrally arranged, and it will have a ionic radii of 1.24 angstrom. But in this rock salt structure, it is in the octahedral geometry, which is it is surrounded by 6 oxygen, and the ionic radii will be much larger than the tetrahedral, 0.8. Now, the Woodside structure is the most stable form, as I already said. Zinc blende can only be stabilized or when if it is grown as a thin film over a cubic lattice structure. Okay, so you have to take a cubic lattice structure as a substrate, and then you should start growing this structure. Okay, then only you can form the zinc type structure. And rock salt structure, I'm going to discuss it later on also, just in 1 or 2 slides. It can be only created at a very high pressure by pressurizing at about, say, 10 GPa, which is approximately 10 ton per centimeter square. Okay, so it's a huge pressure. If you put it on a crystal of woodsite structure, you may achieve the rock salt structure, and that is also temporary. Okay. Now, as I why I am so crazy about structure, because all the properties depend on the structure of the material. You change, so this is a general structure of some molecule. I'm not, this is copper oxide, by the way. Anyway, so you see there are several angles here, and there are several bond lengths associated here. Now, if you change the bond angles even by 0.1 degree, or if you change the bond length by even zero point 0.1 angstrom, a lot of things change. Okay, because the electronic interaction between the two things change, so energy levels change, and that gives rise to a different type of electron. So hence, it is very important to analyze the structure and characterize the properties of each material. So whenever we make some change in a material, we have to be careful what changes have it made. Has it made in the structure, and how is it correlated with the changes of the functionalities that we are observing. Now, as I said, the zinc oxide structure, the zinc has 4 oxygen atoms connected to it. And similarly, the oxygen has 4 zinc atoms connected to it. And if you see it from the top view, then you can see this triangle of the oxygen atoms, the triangle of zinc atoms fall on top of each other. Okay. So this is the another way of representing the zinc oxide structure. So as I mentioned here, the triangles, these triangles are falling on top of each other. Now if you go to the from the wizard, the zinc blade structure, you can see that this triangle no longer is on top of each other in the zinc blend structure. It has actually, the oxygen triangle has moved, has rotated by 60 degrees with respect to the zinc. So these two are different in structure from this. And obviously the bond lengths and bond angles will change. Here you can see the bond lengths are 1.75 and 1.98. So this is one point that I want to make you understand also. In this structure, one of the bond lengths is larger than the other 3 bond lengths. Okay, so these are I will refer to them as zinc oxygen bond along the AB plane, because this is the A axis and the B axis, and this is along the C axis. So this is the zinc oxygen bond along the C axis. The zinc oxygen bond along the C axis is larger than the along the AB axis. Okay, and if you now pressurize this thing, what will happen? This atom will be pushed down, and as a result, this angle 110 will be increased. And if all of them are in a same plane, it should be equally divided. So 180 divided by, 360 divided by 3, that should be 120 degree. Okay. So as much as you push it down, this angle will become larger and larger, and this angle will become smaller and smaller, and ultimately reach 90 degrees. Okay. So this is where we can try to achieve the next I'm coming back to this one, the next thing. So this is the pressure. If you apply pressure, then this may transform to the rock salt structure, which is something like this. Okay, you can see in the rock salt structure, all the angles are 90 degrees, where that one, the angles were different. Okay, and in the rock salt structure, all the bond lengths are also the same. Now let us go back to zinc blende. In the zinc blende structure, you can see the bond lengths have changed. Okay, so all the bond lengths are same here again, and the bond angles are also same. So this is a pretty different type of structure than the woodside structure. Woodside structure has more variance. Here, the variance is less. Okay. Now, now, I already discussed that the angle, there's the angle between the two respective successive oxygen zinc triangles, and I've also discussed this thing. So I hope the structure of these three materials, these three phases, have been well understood by you. Okay. Now, let me go to the solid state reaction. Now, people generally at one time used to make new materials using solid state reaction. Some people, some of the scientists prefer to do it even today. And as you can see, what they do take two different materials. Suppose if I want to make barium titanate, I will take barium oxide and titanium oxide, grind them very well, mix them so that they are in the different components are in touch with each other and they can fuse together very easily. And then we heat them. And what happens, you can see that there is diffusion of one element to the other element and other element to the other. And then a composite type of material is formed, and you keep on repeating, grinding and heating. And ultimately, the expectation is to form a single phase. But in many cases, what happens, the diffusion, after it forms a stable component, suppose you're trying to make barium titanate, not necessarily always you can make barium titanate in one goal or even in multiple goals, because you have in the way, sometimes you can make something like barium Ba2TiO4, which is a different phase. And if there is a minima of formation, energy of formation, then it will get steady in that and it will not try to go to a new phase of barium titanate. Okay. So, but occasionally there are impurity phases by solid state reaction. But people have used it over the years, maybe hundreds of years, and they have been able to obtain decent compositions using this technique also. A way to avoid this type of thing is to ensure that you have a homogeneous mixture of the component elements, okay? That can be achieved by using the component elements as ions in a liquid solution, okay? Or a gaseous solution. So the gaseous solution can be only obtained if you can put a plasma and create a plasma of these ions and make them simultaneously be deposited on some substrate. That's a thin film growth technique. And the general way of doing it is a liquid-based system. There can be several liquid-based systems, out of which I will just discuss the hydrothermal process and the solvent synthesis. In both cases, we take the component elements, some precursors of component elements, which are water soluble or some soluble in some medium, and the common medium, and then we put them in a jar and heat them at high pressure. Okay, that's the hydrothermal process, and that can be achieved by putting a cap, an airtight cap in it, and then heating the entire setup at a higher temperature. The temperature and the components inside determine the phase formation of this material, of the desired material. And that is how people have been able to achieve very nice nanoparticles. Okay, so whenever we think of nanoparticle synthesis and oxides, we think of a hydrothermal process rather than any other process. The sol-gel also provides nanoparticles, but in most cases, sol-gel synthesis arrives at some agglomerated particles, which gives us a little bit of problem to analyze the materials or use them as nanomaterials. Okay? Because the surface charge on these materials make them adhere to each other. As a result, you can get a big chunk of matter, which are actually components of 20 to 30 nanometer, even smaller in some cases. But the crystallites cannot be separated. So if you need separated crystallites, this is not a very good way of doing it. Okay. But solid gel has several advantages. Suppose you want to achieve a definite amount, a definite composition. Solid gel is the best to do it, because then you can take the right amount of the A component and the B component in the perfect ratio and put them inside in the solution, liquid solution, put a polymeric solution in it, and let the ions be homogeneously distributed through the polymers and get attached to the polymers. And by attaching, you are ensuring that the right proportion of these dopant molecules, atoms, are there in the vicinity as you desire. So in order to get a homogeneous solution, you always need a solid gel type of synthesis. So once the polymer has got attached to the ions, you can just dry off the polymer and then burn it off, so leaving the ions behind in the perfect homogeneous condition. And then when you can provide the right energy, you will form the phase after heating it at the temperature. Okay, so this is an example of the solid method. So as I said, the precursors have been mixed here, and then we have added the polymer, and then a sol is prepared, which is a dense form of the solution, and a pre-gel form of the solution. Okay, and after that, a jelly-like appearance appears, and then if we burn this gel, then we find that the polymers are basically chains of carbon, hydrogen, and nitrogen. So the lot of nitrogen dioxide, carbon monoxide, water vapor is evolved, and we are finally left with some sort of powders. It can be this type or it can be this type. And then we put it in the furnace, and then we get the right composition. That is the way we make the samples using solvent. Now, after that, as I said, we use the X-ray diffraction diffractometer. The X-ray diffractometer uses X-rays as the probe of understanding the structure. The structure, actually, any light structure is comprised of different planes. The crystal structure, crystals all have different sets of atoms arranged regularly. So there is a separation between a set of atoms and the next level of the set of atoms. And these are called planes. And when light falls on these planes, they get scattered by the scattering atoms that are present on those planes. And these scattered components of the light reunite using some interference laws, and that is given by Bragg's law, and that will in lambda, when the condition in lambda is equal to 2d sine theta, but theta is the angle of reflection here. So, and 2 theta is the angle of deviation. So if you extrapolate this line, then this angle will be also theta. So 2 theta will be the angle of deviation of the light that was incident and the angle of diffracted light. So, so when this condition is satisfied, we'll get a constructive interference and we'll have a maximum peak. So depending on the lambda that you're using and the theta that you are getting, you can calculate the d-spacings. And by calculating the d-spacings, you can know what are the crystalline plane, and that we can do refinement using which is called Rydberg refinement. I don't know how to read this in my video. Yeah. So yeah. So Rydberg refinement, which is a method developed by the scientist, Dutch scientist Hugo M. Rydberg, back in the 1950s, 60s sometime. And then after that, we have a very good understanding of how the structure looks like. Okay. Now, in a crystallographic structure, we generally define an unit cell that is a repetitive cell, and that consists of three different axes, as I previously showed, A axis, B axis, and C axis, and three different angles. That gives rise to lots of space groups that we encounter in our daily life while studying materials. And from the peak position, we get an estimation of the unit cell parameters. And from the peak intensity, we get the atomic parameters. And the peak shape, we get the crystallinity, disorder, or defects. Okay, I'll come to it in the next slide. Okay. Now, there can be a lot of things to say about these things. Ritual refinement is a very strong and powerful refinement technique. And there are several softwares that are used today, including Prof, Topaz, GSAS. GSAS is, GSAS is very well accepted. Prof is very well accepted. And we use Prof and GSAS in our lab to understand the structure of this of our synthesized materials. Okay. Now, what the refinement looks like. So the black points, the cross ones, are the experimental data, and you can see we have fitted the experimental data with our refinement, and we can find that it has fitted very well. And the residue is given by the difference between the theory and the experiment is given by this blue line. So this is pretty good fitting, and we have achieved a chi-square of and generally a good fit gives you a chi-square. Chi-square means the least square difference, which is about 2 to 3. That is considered as a good one. And from that, we can find out the lattice constants. And we can also find the crystallite size and the strain that is present in the lattice. Okay. Now the Scherer's formula can be used to find out the here beta is the full width half maxima, and D is the crystallite size. So the crystallite size that you are seeing here, this is the crystallite size. It shows that the crystallite size has gone down with substitution. We have tried to substitute, in this case, it's manganese in zinc oxide, and with it has gone down. Now, why does crystallite size go down? Because a crystal grows if a long range order can be maintained in the material. Okay. Now, when it comes to order, if you keep on introducing new materials in something, then what happens? You are creating you are putting in different ionic size and different ionic charge into the material. Even if it is the same ionic charge, it can be, in most cases, it is a different ionic radii. Okay. And when it is a different ionic radii, if it is bigger, it will push the oxygen atoms surrounding it away from it. If it is smaller, then it will try to pull the oxygen atoms towards it. As a result, there will be some strain generated in the lattice. And that gives rise to disruption of the long range order. And that's how the crystallite size decreases. So the Williamson-Hall effect is also is a way to measure the strain, which is epsilon, and that is the induced strain. And we can then, using these two formulas. So this beta is the full width half maxima, and theta is the angle. So by having an accountable data, we can find out D and epsilon. Okay. So this is how X-ray diffraction data can be used to calculate these parameters if the materials are nano in nature, that is lesser than 100. The most important technique that we use to characterize any material is spectroscopy. Spectroscopy is a very broad word, and what it means there is some sort of absorption of a specific excitation. It can be it's a type of light that is incident on it, and it can be various types of light. Okay? and what the light can do to the material and how the material responds to the light is the matter of importance, and that's how we understand the properties of the material. So whenever some light is falling on some materials, there are different states. It can be vibrational state, it can be electronic state, and due to those states, there will be absorption of that light, and and the states, I call it states here because it can be an electron, it can be a vibrational state, can transit to a higher energy state, and then it can get absorbed. And when it comes back, if it gives back the same energy, or it can transit to a different energy level, which is available inside, and in between these two levels, then we can have an estimation of all those energy states. Okay, so we can do fluorescence, we can do absorption, we can do phosphorescence, we can do Raman scattering, etc. Now, talking of spectroscopy, I like to concentrate its spectroscopy. The first thing which comes is X-ray fluorescence. So what is X-ray fluorescence? Suppose you shine an X-ray on an atom. I do not know what atom it is. Now, if this X-ray has enough energy to strike off or impart that much energy that can knock this electron out, then what happens? Then this electron from the core level gets knocked off and leaving a hole behind, right? Now, when the hole is left behind, the higher electrons in the higher orbits, they will try to go to a lower energy state, and they will transit to this space which is vacant. And in doing so, it has to lose some of its energy. And when it loses, it is losing energy just in the quanta. Okay, it is a discrete. It is the energy which is the difference between these two discrete levels. Okay, so this energy is very specified for one element. Okay, so we have several elements, and we can guarantee that only in rare cases the energies are very close to each other. In most cases, they are far away from each other, and that gives us the privilege of understanding what type of components or elements the composition of the sample has. So this is a typical XRF of a material, and it shows that it has copper, it has titanium, it has manganese, it has gold, it has nickel, lead, and etc. Okay, so now this is a powerful technique because these energies are very easily detectable. You can see how sharp these transitions are and these peaks are. So by seeing these peaks, we can we know the energies that are related to these positions, these energies, and then we can say, okay, this element is present. So this is a schematic of how XRF works. There's a X-ray source which falls on some optics, and then the optics, what it does is focuses on the beam onto the sample, and then again the beam gets scattered from the sample, and then it falls on another converging optics, which converges the entire signal to a detector, and the detector analyzes this spectrum. Okay. Now, this type of analysis can also be done using an electron microscope. The electron microscope, instead of using an X-ray source, it uses an electron gun. So the electron gun actually emits electrons with certain amount of energy, and those electrons are accelerated through different magnetic lenses and anodes, and then there are scanning coils which can control the properties of these electrons, and ultimately the electrons fall on the sample which is here. And what happens, there are electrons which are scattered back, so back scattered electrons. Okay, And then there are secondary electrons which are also emitted. I can tell you what about these things are. So if a primary electron comes, then this electron can take out the electron from the orbit, then a secondary electron is emitted. And if the primary electron is affected by the nucleus, this like something like Rutherford's backscattering. So that's why it's called backscattered electron. So this in Rutherford uh, experiment, we use a different particle. I hope you guys know about it. And here we are using electrons. Okay, so the electron passes through the nucleus, past the nucleus. Instead of colliding with it, it just gets deviated and comes back. And so the backscattered electrons are just on top, try to come back in the same path. Okay, so and they're collected by this detector. Okay, so this is what happens here now. And then when the primary electron, it takes away core electrons, then there is a chance that the X-ray is emitted. As I said in this previous one, the X-ray is emitted when the electron goes from the higher level to the core level. The same thing happens here but here we are using an electron instead of X-ray, and it's doing the same thing. A secondary electron is emitted from a core level, and as a result, an X-ray is emitted, which is characteristic of the difference between the levels. So from these X-rays, we can also understand what the element is. So we always have a energy, energy spectroscopy unit associated with all electron microscopes, and we can find out very nice data. Instead of doing X-ray, we can get that same data from here. Okay. Now, what the electron microscope can give us, it can give us the morphology of the materials. And from the morphology, we can understand whether the particles are agglomerated, how big are the particles. In from X-ray diffraction, we could understand the crystallite size of the materials. Okay, that by crystallite size, we mean how long the crystal is in one piece. Okay, so in one regular lattice. Okay, but here we can think about how big the particles can be. In these particles, suppose there can be several crystallites embedded. We do not know, because you can see here there are small particles, and maybe they were fused and formed such a particle here. So those particles are not visible. They are oriented in different directions. But as a whole, this particle, how big the particles become after fusion of these crystallites, that estimation can be obtained from this. And also, it can give you from the EDX scans, it can give you the chemical homogeneity of the materials. So, so this is a zinc scan. So we have done we have chosen the position of say this energy, and we try to find out how the zinc is distributed throughout the thing. And if the material is homogeneous, we should get a very equal distribution of zinc, gallium, or the dopants. Okay. So this is how we can find out the homogeneity of the materials. Okay. So the FESM can give us morphology, the chemical composition, to some extent, ballpark extent. Yes, no, not a precise way of looking into the chemical composition, but yes, it can give you what components are there and what can it be. Means it has, if you have not no barium in zinc oxide, the barium should not be there. If it is there, then you have contaminated it with some other source. That information is available from EDX and FESM. And as I said, the chemical homogeneity. So these are some materials that has been created in my lab. You can see these are agglomerated particles. These are crystallites here. And then there are nanorod type, pillar type thing, which are originating from one point here. So often what happens, there are seeds which are coagulate like this. And then when you keep on growing these materials, then they will grow according to the crystal orientation that is available on these particles. So it grows to different rods, giving rise to this type of behavior. And then there are certain examples where there are crystallographic orientations in layers. Okay, so this is a material where the crystals have grown in one particular direction, but they are separated by layers for some reason. Okay, that needs to be. Another important experiment with the electron microscope is the transmission electron microscope. What it does, it takes, we have to make very thin samples or powder samples, which are nano in size. We have to put them on a TM grid, a transmission electron microscope grid, which is basically a copper grid. And there are certain membranes that are placed on those transparent membranes, which does not give a diffraction pattern if the electron passes through. Remember, electrons and X-rays can diffract from matter, okay, if the matter has a regular lattice, okay. So we use some non-crystalline membrane on which we can put some of our crystalline material and make the electrons pass through those thin crystal layers and diffract according to the arrangement of the atoms. And what we can find that this is an ideal example I keep on taking. You can see there is a crystallite here, a big crystallite, and then there's another big crystallite with thousands of atoms arranged properly in this domain. And then there is another region where the domain has changed here. So this gamma 3 region. So the orientation has changed. So it's part of the same crystallite particle, but it is a different crystallite. There is a difference of the domains that are available. So all these types of crystallographic defects. Okay, so you can see when this type of crystallographic reorientation has taken place, there is a region often obtained where there is some turbulence in the regularity of the material. So this type of information can be obtained from HRTM, high resolution transmission electron microscope. Obviously, the EDX can also be done. What we can do, we can take a specific area where the regularity is there and Fourier transform the data, and we can get diffraction pattern like this. This is a typical Lau type diffraction pattern as we obtain from X-ray diffraction. We can do a similar analysis on diffraction too. And that is how the X-ray diffractometer and this transmission, this is called selected area diffraction in electron microscopy system. So these are some examples of how my samples, you can see there is crystallographic defects here, and you can see there is one region, and then there's a striped region here, and again another striped region. So there's a continuous discontinuity of this. This is a ferroelectric material, by the way, and the ferroelectricity is compelling the domains to keep on switching and their orientation. Okay, now the study of crystallographic faults at atomic level, as I said, can be obtained. The crystallographic structure at the atomic level, that is also possible. In X-ray diffraction, you cannot do it at the atomic level because atomic level information is not obtained. But here you can take a diffraction pattern of 1 grain and then understand what is the atomic structure in this thing. Okay, then the crystallite size can be obtained from those images, and then the grain boundaries, terminating edges. What are the terminating edges? Suppose this one, what is the edge? By calculating this d-spacing, we can find out which d-spacing is this, and then we can find out which it corresponds to which plane. So then we can find out which is the terminating edge of these nanoparticles, okay? And then the chemical composition and homogeneity and the morphology at the nanoscale that can be found out, okay? Now we come to another very important aspect to understand the charge state. Okay, I'll complete this, okay? Okay. So X-ray photoelectron spectroscopy is a very important technique. So what it does, it shines X-rays, and these are photons falling on the surface of the material. And what happens, there is ejection of photoelectrons. And now we can analyze these photoelectrons using different analyzers. And the most common one is nowadays is concentric hemispheric analyzer, commonly called CHA. The analyzer, what it does, it analyzes the energy of these electrons, the kinetic energy. And the kinetic energy that is measured, you know the energy of the photon, you know that you have measured the kinetic energy, and you want to know the binding energy that is of these electrons. And then you can find out the specific property of these binding energies. Now, the binding energy gives us the information of the charge state of those elements, or even if there's a, say, oxygen vacancy in these materials, you can check on that. So if there's oxygen vacancy, the energy states of these things, of these states will change. If the charge state of the ion has changed, then the binding energy will change. Okay, because there is some electrostatic and more covalent bonding that is that will determine the binding energy. Okay, so by knowing the binding energy, we can assess how what are the different components of the elements that you have put. Suppose you put manganese. Manganese can be in 2+, 3+, and 4+ state. What is the percentage of 2+, or what is the percentage of 3+, or what is the percentage of 4+? That can be found out by X-ray photoelectron spectroscopy. So this is a typical graph of showing the absorption of the energies. So where the binding energy is high, you can find out that you can see there's a rise of the thing. So this binding energy is present. So by analyzing these binding energies, you can find out what type of, this is a typical example which I show. There can be lattice oxygen in the material. This can be oxygen vacancy, or there can be oxygen which is, but it is chemically absorbed on the surface or something like that. Okay, so those components you can follow up and find how, if you chemically modify this material, how this chemical modification has altered these components of oxygen in the oxide material. So this type of things can be well studied using for X-ray photoelectron spectroscopy. Okay, now to my before I end in this session. Okay, so X-ray absorption spectroscopy is a similar thing, that but similar information that we get, but it's a different technique. Okay, in X-ray absorption spectroscopy, what we do, we shine X-rays on the material, and we allow the same process of electron being ejected from the core shells, and we get the absorption. So we shine the light, we see how much light has been absorbed. So if it corresponds to the difference of the energy, or that energy that is needed for the electron to get thrown away from the shell, we can understand that there is an absorption. So this energy is being absorbed. So before that energy is being provided, there is nothing. But when you provide that much of energy, that gives rise to some absorption. And the absorption continues, because suppose you provide this energy, which is just enough to make it escape, it is fine that it gets absorbed, that energy. But it can also, if you provide a little bit more, it will also get thrown out, right? So it keeps on going like that. Okay. Now, what happens in this type of thing, in this type of absorption energy? So you have the other electrons which are in the higher state, they come back and then they emit some light, right? And that light will be exactly proportional to the difference between the, equal to the difference between the two energy states. That energy, when it comes out in form of X-rays, and those X-rays can excite the neighboring atoms, okay? And when it excites the neighboring atoms, there is scattering from those atoms, and soon there will be an interference of pattern observed between the scattered and the scattered components, okay, X-rays. Now, this scatter, the interference pattern can be observed in this extended part of the absorption spectra. So if you take this absorption spectra and do a Fourier transform of it, first we have to change the energy to momentum space and then do a Fourier transform. Then we can get some, God, where is it? Okay, sorry, I forgot to put that one. So then you can get a exact pattern, which is the in real space. So that will give you the distance between the atoms that are in the immediate neighborhood of these atoms. So it can give you the structure. So like Rydberg refinement, this also can be refined. The structure can be refined. So you take a crystallographic index file as much as you do in the Rydberg refinement while doing the refinement, and put it in this type of software, and you study the interference pattern and get the information of the distances that are available in between these things. Okay. The last thing that I wanted to say: suppose there is a distortion in some octahedra or a tetrahedra, those type of distortions which are undue in the material or is not supposed to happen, but due to the structural modification, you have generated something, then they create different types of energy level, which may be just ahead of the absorption energy of these things. These are called pH, and all sorts of distorted energies can be understood by studying the pH. There is a huge group of scientists working on this type of Zen's data, and we get a lot of information about the charge state, about the distortions in the lattice from the Zens and Exas data. So I will end this part of the thing here, and I'll start with UV visible spectroscopy from the next chapter. Okay.
Thank you so much, sir. It was really very effective and beautifully delivered presentation. Now, without wasting any much time, I would like to take questions that our participants have posted in the chat box.
Oh, yes.
So the first question is, sir, from Dr. Nishan Gaur, and he's asking, can we connect your research with binary alloys and nano alloys?
Okay, very good. Yeah, means recently I have started thinking about getting into some alloy semiconductor research interface related to magnetic thin films. Okay, so if someone can think of some magnetic thin films, then I am very much interested in going into a collaboration. Yeah.
Thank you, sir. Next question is from Ms. Farhadiba, and she's asking, could you please explain what is the reason for the increase in particle size in sol gel synthesis using PVA as surfactant?
Oh, okay, very good. Okay. So when you see, it's all about the when you heat something, what you are doing, you are trying to grow the nanoparticles, assuming some of them are smaller in size and some of them are larger in size. Okay. So when nucleation happens, it does not happen. Suppose when we start our solute synthesis, at some point the nucleation starts to happen. Now, when it starts to happen, it is not obvious that all nucleations will start at the same point. As a result, what happens, there is a time lag between nucleation processes to start and giving rise to differences in the size distribution. Now, it is known that a smaller particle can be swallowed by a larger particle. The larger particle has much precise long-range order, and it has the tendency of absorbing more atoms towards its regular distribution. Okay, so the smaller particles generally gradually come into contact with these things, the bigger ones, and they get absorbed. So that They get eaten up by the bigger ones. Now, when you add PVA, the PVA is a binder which this facilitates this process. Okay. So the PVA itself does not take part in the reaction, but as it has brought these two particles in contact to each other, it is easier for the the bigger particles to swallow up these smaller ones.
Thank you, sir. Next question is from Ramya Nair, and she's asking, sir, for spectroscopy, which light source and tool is used in your lab, laser or a spectrometer?
No, we do not use a laser. We use a broadband source for, I'll come to it. I've not talked about it yet. The X-ray, the XRD that we have is a different component. It obviously needs a monochromatic X-ray source. And you know, this is the X-ray tube that construction is known to most of you, I believe. But other than that, we have a UV spectrometer, which in which we use two different light sources for the UV and the white light.
Thank you so much, sir. Yes, sir. Thank you so much, sir. With this, I declare the end of the session 1. So, dear participants, I request all of you to please join back again at 1:30 p.m. for the second lecture of Professor Sen. Thank you so much, everyone, for joining.
Thank you.
Thank you so much, sir.